Previously, we connected an I2C sensor to our development board and then used the Yocto project to enable an I2C port in the device tree. Now, let's create a quick application that reads temperature data from that sensor and then simply prints it to the console. Here are the connections that we made last time. I connected 3.3 volts to VIN on the sensor breakout board, SDA to SDA, SCL to SCL, and of course ground to ground. We're using I2C port 5 on the STM32MP157D-DK1. Yocto has a software development kit, or SDK, and this can help you debug and integrate your program into an image. If you look through this documentation, which I highly recommend reading if you're curious about using the SDK, to see how you might set it up and how it works. There's an Eclipse plugin that you can use to help you during development to create and debug your custom application that gets built into a custom image. Feel free to look through the flowchart, read through this documentation, and I do recommend using this SDK when you go to do application as well as kernel development for your specific device. I'm going to skip this for now as I want to show you how to include an application in your image manually. Another option is to develop on a similar embedded Linux computer that has all of the development tools installed. For example, I used my Raspberry Pi to develop the program I'm about to show you, as it has GCC already installed to let me compile on the device itself. I might recommend using your target device, like the STM32MP157D-DK1, with a different image OS configured with your required build and debugging tools. I recommend checking the vendor site for your particular board. For example, ST has an SDK built specifically for the STM32MP1 series. This can help give you easier access to parts on the board and to communicate with various ports such as SPI and I2C. That being said, I'm going to show you how to do things the hard way so you can get an idea of how you might build and deploy a custom application with your image. We're going to create a very simple C application that exists in our custom layer that we made in a previous episode. As you'll probably notice by now, these custom layers can be used to hold a variety of different information or metadata. This could be recipes to build a specific image, it could be source code for custom applications, or it could include kernel modules. A layer is a good place to store these things, especially if you're modifying or creating your own custom image that's going to be deployed to a device, say, during production. To begin, let's head to our custom layer, which I keep in Projects Yocto Meta Custom. In our custom layer, we're going to create a new directory structure that holds recipes for our custom applications. In this case, we're going to have recipes apps be our first directory, and in there we're going to have another directory that is mytemp, and that's where we're going to store the custom application where we will read from the I2C sensor and then just print the temperature to the screen or to the console. Let's go into that directory, and here we're going to want to make a source folder where we keep our source code files. Alternatively, you could have a separate GitHub repository where your source code lives, and then you use a recipe, a Yocto project recipe, to download source code from that repo. And this is useful if you want to develop an application that works across a variety of different boards, like a Raspberry Pi, your STM32MP1, a BeagleBone Black. That application works, maybe with some minor settings or tweaks, and then you just use your recipe here, or you use your recipe in your custom layer to download from that GitHub repository. However, we're going to keep things locally right now, and BitBake can look for source files in a variety of locations. One of them can be locally, another could be somewhere on the internet, say a GitHub repo with the custom application that you've created. Now we're going to write the program, and we're going to do so in this gettemp.c file. The first thing we need to do in our program is to include a bunch of header files which are linked to libraries, most of which should come with Linux. Even in the core image minimal where we don't have a lot, many of these libraries are baked into the kernel so that we can do things like print to the console or work with an I2C device file. We're going to use some constants that we discovered in the last episode. Specifically, the address of the TMP102 sensor is hex 48, as we saw when we did I2C detect on the bus. We just have to remember that we did I2C detect, wrote down or remembered hex 48, and we're going to use that as the address here. That allows us to talk to the sensor. Next, we have the address of the temperature register, which is where we can read the temperature from. To get that, we look at the datasheet for the TMP102. We go to Programming, we go to Pointer Register, and by changing this register here, we can access the other registers that are on this device. As you can see, there are not too many of them. The first one, 00, that's the address we're reading from, is the temperature register, and that is read-only. This should give us 2 bytes of information when we read from the I2C device, and we can combine those 2 bytes to get some sort of temperature in Celsius. Finally, we have the I2C device file itself, which is at dev i2c-1. We enabled that device file in the previous episode, and that points to the actual location of I2C port 5, which is where we have the TMP102 connected. Then we're going to need some variables in our program. We need a handle to the file that we're about to open, because in order to work with that I2C device file, we do it with a file like we would with any file in Linux. We then need a small buffer so that we can send and receive data to and from the TMP102. Then we have a temperature buffer, which we're going to use to do a little math to get our temperature in Celsius, which we will store in a floating point variable. Next, we're going to open the device file using the Linux open command that comes with one of our standard libraries, and we're going to store a handle in that file variable. We're going to open it for reading and writing, since we're going to need to both read and write to the device in order to communicate over I2C. If we cannot open that file, that means something's wrong, whether something didn't enumerate correctly, that I2C-1 file isn't available, we don't have permissions, we're just going to get an error message saying that it failed to open the bus. Note that as I'm doing this and showing you this, feel free to remove everything I'm showing you in main and just do a printf hello world followed by a return 0 if you want to create your own hello world application because you don't want to deal with any of this I2C stuff. That should also work if you just want to try creating your own basic application here. To work with a device file such as our I2C device file, we need to change the address of it using the IO control function so that it points to the I2C device's address. In this case, we're changing it to hex 48 inside that file, so then when we go to read and write that file, it sends out commands to that particular device on the bus. Next, we start the read process by writing the location of the temperature sensor. And we do that by writing the address out on the line using the write command. In this case, we write to the file using our buffer, and we give it the number of bytes from that buffer to write out to the file. In this case, that gets written out to the I2C lines. If the write command fails, it should return something other than 1. In this case, we will just print an error message and exit out of the application. Notice that I'm using exit here and not return. Exit is something specific to the Linux operating system that tells the calling process that, hey, we're done with this, you need to exit, and I believe exit 1 says exit with an error. Something went wrong when we exited out of this program. Once we finish that writing command, we then read from the file. In this case, we tell it to read 2 bytes and store those 2 bytes into our buffer. The number of bytes read, and I believe this is the case for writing 2, should be returned. So if we write 1 byte to the file, the function should return 1, and that's why we're checking against 1. If we expect to read 2 bytes, the function should return the number 2, which is why we're checking against the number 2. If we don't get that, that means something went wrong and we could not read from that device file. In case you're curious where I'm getting this information about how to read and write to this TMP102, I'm looking at the datasheet. And what you want to look for are these 2-wire or I2C timing diagrams that tell you how to read and write to this device. We send out the address and then we send out the register address, and then from there we can read however many bytes from that address in a consecutive fashion, which is how we can read 2 bytes that give us the temperature information. We can then combine those 2 bytes that we read in from the temperature register to a single 16-bit value. Feel free to look at the data sheet to see how to do this, but all we're going to do is shift that first byte to the left by 4 bits, shift the second byte to the right by 4 bits, and next we need to combine them in such a fashion that we handle negative values. The temperature coming out of the sensor is a 12-bit value. If that first bit is 1, then we know it's a negative value. So after we shift that first byte over by 4 bits, we basically check to see if that first bit is 1 by comparing the entire value to hex 7FF. If that returns it's greater than that, which means that first bit is 1, we then pad the remaining empty 4 bits that's at the beginning of those 16 bits with 1s. And then that will basically trick the program to thinking that this is a negative number, and we get the correct negative Celsius value out of this. Note that that 16-bit integer value is not exactly Celsius. It can be converted to Celsius fairly easily by multiplying it by 0.0625. That gives us a floating point value that should be a very close approximation of what is the ambient temperature around that sensor. When we're done, we can print that floating point value to the console just so that when we call this program, it just gives us the temperature, and then we return 0 to say that the program finished and there were no errors. Feel free to delete everything above this line in this main function and just have printf hello world if you just want to try something super basic in order to see how to cross-compile and include this application into your custom image. But I'm going to take it up to the next level to show you how you can read from the I2C bus that we implemented or enabled in the previous episode. When you are done, save and exit. And hopefully you can see that this is quite a pain to do in VI, which is why I recommend setting up some other development environment that we won't get into in this series, such as Eclipse using the Yocto SDK, or some other way to develop this, because doing everything with VI, cross-compiling, building into an image, and then seeing if it works on your target device is a terrible way to debug your program. But this is just showing you how you can create a simple program and then include it in the build process. If you remember when we created our custom layer, Yocto gave us this example recipe that we could look at. So let's take a look at it, and you see a template that we can use to construct our own recipe that gets baked into our image. You'll see that it has a license shown here. Yocto is very particular about licenses, so that when we create our own recipe, we really should include a very specific license. We can make up our own or even have it closed source if we want to, but a license does need to be present in the recipe. If you go to the Poki reference distribution, look in meta, files, common licenses, you get a list of licenses that are available. Now remember, you can still close source something, or you can create your own license, but you would want to add it and get a hash. We're going to use the MIT license, which is readily available for us here. Feel free to look at that license. If you're familiar with the MIT license, they should look very similar to what you've seen before. And note that to use it in our own recipe, I highly recommend using the MD5 sum to get the MD5 hash of that. We're going to use this in case the license ever changes. This hash would be different, and Yocto, or BitBake rather, compares it to the hash of this file to make sure we're using a real known good license. And you can create your own license and create your own hash, which is fine, but we're going to use an existing license for this. Keep in mind that we're still in recipes apps. mytemp, we're going to create our own recipe in the mytemp folder. And it's going to be the name of the recipe, gettemp underscore version number. For me, it's going to be 0.1 and .bb, which means it's a recipe. You will want to copy that license file and save it somewhere for now. We're going to need it when we're writing this recipe. I recommend starting off with a basic summary of what your recipe does. This is a recipe for the get temperature application. We'll then give it a description where you can flesh out what this particular recipe does. You'll want to call out which license you're using. And then for our purposes, we will want to point out where that license file is. Yocto maintains this common license directory variable so that it knows where to find those license files that we were just looking at, and we will specifically call out the MIT license that's located in there. From there, we'll give it an MD5 hash number so that it knows that it lines up with that file and nothing has changed. And this is where we're going to go and copy our MD5 hash. We should be able to paste it in there. The next thing we want to do is define this source URI variable, and we will tell it where to find our source files, specifically that gettemp.c file that we just created. And you'll notice that this URI variable can be really any location. This could be a local, which is what we're doing to get that source file. It could also be a GitHub repository or an FTP server where it's pulling in, it's telling Yocto or BitBake to pull in a file from some location, and that can be local, remotely, what have you. In this case, we're calling out this src directory, but note that src needs to be in files if it's going to look locally in our recipe directory, this mytemp directory, and search for files relative to this path. But notice that it won't search necessarily in mytemp, it's going to look in mytemp/files. That's kind of a given with this source URI. So if we want to look in files and some other directory in files, we need to specify it here. And that's where it's going to find this src directory, which is why it's mytemp/files/src, and that's where our .c file is. When BitBake runs this recipe, it's going to look for the files that we specify with this source URI, and it's going to download them into a working directory. And remember that this working directory exists within temp in our build directory. That's build-mp1 that we have created. That's part of the reason why Yocto takes up so much space, is because it copies everything locally to this working directory, all the source code, then it builds all the image files, libraries, packages, and modules, and it just takes up a ton of space on your hard drive to do this, but it gives us a lot of control in how Linux is being built. One thing I noticed with recent versions of the Yocto project is that it forces us to pass this LD flags variable to the target CC arc or arch variable. And we're just going to append them with the plus equals to this variable so that when the linker is called, any flags set in LD flags are passed in to that build step. This is necessary. BitBake fails if you don't do this, even if LD flags is empty, which we're going to leave empty right now. As far as I know, I'm not setting them anywhere, but this step is necessary. When BitBake runs a recipe, it executes a series of functions. One of those functions is this do compile step, and it calls anything that's inside this function. In our case, we're going to call GCC, which is the given compiler, or specifically the cross compiler for GCC ARM. And that's going to pull in our gettemp.c source code. That's going to compile it to the gettemp binary that we can call in Linux, hopefully on our target device. So this should not run on the host machine. We're using a cross compiler to do this. This is a very, very simple example of how we can use GCC to compile a single source file. Obviously, as you get more into development, this is going to grow much larger, and you can have do compile work with things like make files or CMake into make files or any sort of these build systems you'd like, and you can have it call the whole make system here, which makes this process a lot easier because you can develop on, say, another system. If make runs there, you can set up make to run here in this do compile step. after compiling the program or programs, BitBake will run this do install step if anything is in here. In this case, we are telling it we want to install our program in the bin directory, which is user bin on our target device that's part of the root file system. It should copy this git temp to user bin, which will give us access to run it as an application. You also want to change the permissions of this particular file or application. I'm going to do 755 so that basically everybody has access to it. Then I'm going to change the permissions of the git temp file so that root, I guess the owner in this case, can read and write to it, as well as give permissions so that I think everybody can execute it if you happen to have more users on the system, if I remember what 755 does. From there, let's save and exit out of this file. Now that we have our git temp recipe created, we want to include that recipe in our custom image so that BitBake will call this recipe during the build process. If you remember, we created our custom image in recipes core during an earlier episode. And our custom image is named, well, custom image, and we have this .bb recipe that gets run when we're creating our image. To add our custom application, we're going to append the application name to the end of this recipe. Remember that image install includes all of the different packages that gets installed in the image creation process, so we can just append git temp, which is the name of that recipe minus the version number, in this image recipe. Let's save and exit out of that file, and we should be ready to build at this point. Prior to building, remember that we need to enable our build environment. To do that, we call source pokeoinit build-env and give it the build directory that we already have set up from previous episodes. And if you remember, bblayers.conf contains our meta custom layer, which should contain our image that's going to call the recipe for building our application and installing it in that image. At this point, we're ready to call BitBake custom image to build our image. This might take a little bit of time. I don't believe it will take very long, simply because the only thing we should be changing is an application that's included in the root file system. We should not need to rebuild the entire kernel for this. It looks like I have an error that I will go fix right now. And looking at this, anytime you define variables in Yocto, they need to be treated as strings, basically. So I forgot to include my quotation marks, it looks like. So we'll head to the file given by this error message. And sure enough, I forgot quotation marks in my S variable. As you can see, all the assignments for these other variables have quotation marks. So we'll just give quotation marks around this S variable here. We will save and exit, and we will try running BitBake again. Hopefully this works a little better this time. Sure enough, it looks like everything parsed correctly, and now it's rebuilding only the parts that are needed. In this case, hopefully it's just building and including our custom application. Hopefully you didn't see any more errors during the build process. One thing you can do is check the root file system that should have been baked into the image by going to temp, work, stm32mp1, Poke Linux, GNU EABI, the name of your image, in this case custom image, I believe that's the version number, root fs, and then we're going to look in user bin. If you look through here, you should see all of the available programs, applications, and tools that you can call, and with any luck, we should see git temp that was baked into this during the build process. That means that it compiled correctly, we didn't see any compilation errors, and it installed correctly because it was copied to user bin. At this point, we are ready to flash our SD card. So plug it into your host machine. Let's unmount the partitions that get auto-mounted. Feel free to take a look at the partitions that are available. These are the ones that we set up in an earlier episode. And we're going to use the dd command to copy the root file system to the 5th partition of our SD card. Note that we're using custom-image. That is the name of the image that we created. We should not need to copy the boot file system, as I don't believe anything has changed. We didn't make any changes to the kernel, the boot process, kernel modules, like we did in the previous episode. So in this case, we should just need to copy the root file system to that fifth partition, and when Linux boots, it will give us access, or it will mount that root file system and give us access to the tools that come with it, including our new custom application. Once it's done, remove the SD card from your host machine and plug it into your target dev board. I'm going to open a new tab and use PicoCom to log into the device, or get a console into the device, and then I will apply power to my dev board. We should see Linux booting up, and give it just a second here. And with any luck, we should be presented with a login prompt. We only have one user, and that's root, and password is still TOOR that we set last time. And if we look in user bin, we should see our git temp application that should be installed, which means we don't need to call it from here. We can call it from anywhere. So we just say git temp, and with any luck, our program runs. It reads from that I2C device and gives us the ambient temperature. Feel free to run this a whole bunch. You can breathe on the device or put it near something warm or something cold. I recommend not getting it wet, and you can watch it change. When you're done, I recommend doing a shutdown now to make sure that your target board shuts down nicely and it finishes reading or writing any files so you don't corrupt the file system. I believe that the ext4 format has journaling, so you have less risk of this happening, but this is still a good practice to get in the habit of doing. I hope this gives you an idea of how to begin creating custom applications and then using BitBake to include those applications in your Linux image. Next time, I'll show you how to enable various kernel modules to get Wi-Fi working. See you then!